beyond comprehension.
Yeah, I guess for this event, and it was just oriented right. I guess you had a good upper level trough, kind of right across the South Plains, with winds ripping out of the southwest. Which, when you have winds like that, and it's rounding sort of the bottom of a trough, you get a lot of upper level divergence, which simply just means air is moving, kind of vacating an area up in the atmosphere. Um, which leads to a lot more upward motion at the surface, right? Because if you clear a space of something that's there, something has to come back in to fill that void, right? So you get more upward motion at the surface. That coupled with the moisture for this event arrived kind of right on time. Like
Hmm.
it was right.
Yes.
Dew points in Norman didn't hit into the 60s until very late in the afternoon. It was a You just have all this southerly wind getting pulled from this low pressure system coming through. That what happens is you get moisture that's down by the Gulf of Mexico pulled across Texas from where Ben is. So you can thank Ben for this severe event
Yeah,
technically.
you can thank me, and you can thank the Southern California of Texas for your severe weather.
Yeah,
That's
so all that moisture gets drawn northwards, and that moisture was essentially fuel for the storms. You can't have storms if the atmosphere is too dry. And what we had initially out in western Texas, it's called a dry line. And what happens is, just due to the circulation around a low pressure system and sort of the way the boundaries form, you get some really warm, dry air in behind this
Mhm.
dry line, kind of with winds coming like this. And then out ahead of it, you'll have southeasterly winds that's more warm and water laden air that'll come. And when they intersect, right, it happens right on that boundary. And it's called convergence. And what convergence does is it pushes air upwards, which is what helps initiate thunderstorms. Now, we also had a cold front crashing down behind that. That is what created the QLCS Squall line event. As it overtook the dry line and moved east of it, it became the primary convergence zone for these storms and led to a lot more linear storm motion going up along it.
Yeah, you're spot on with all of that. One of the things to me that was interesting was, like you mentioned, the moisture. We had, at least here in Lubbock, we had winds from the southeast like 20 to 25 miles an hour, and everything. So, like, again, just pulling all that Gulf moisture up into the area, making it readily available. But then on the flip side of that, when the system did pass and we had that dry line, that, uh, kind of the packing on that, again, the winds through our area were so severe, like 40, 45 miles an hour sustained, gusts
When the
like,
wind comes racing down the plains.
yeah. And so, similarly, what that did was it really packed that dry line in there. Like such a distinct boundary. Sometimes when the boundaries are more messy, um, if they're not as definitive, you could say, you don't get the sort of lifting action that you do with like those really tight, really packed boundaries.
Yeah, I think I saw from the official Lubbock Ob after the dry line pushed through, relative humidity plummeted to like
Mhm.
10%.
Yeah, so we can actually take a look at that. Um, so, keeping with the severe thunderstorm track,
And Ben, if you have anything to add, feel free to
yes,
jump
please
in.
do.
We don't want to be hogging all the airtime here.
So this is the sounding from Norman, OU sounding at three, 3 Z.
Oh man. So this is for some context. This sounding was taken. Whoever had the foresight to put this sounding out is a genius, because
Mm-hmm.
this sounding went out about 20 minutes before the tornado touched down in Norman. And when I say this is one of the most fascinating soundings I've ever seen, I mean it.
Mm-hmm.
I mean, it's incredible.
We talk about our one of the professors we had an all star sounding project. We've talked about it a few times, but This
This is one.
deserves to be one.
This is one that will
This
be.
deserves to be one.
He'd be slamming his fist for that EML there.
Uh-huh. So Ben, why don't you take this one?
Oh, talk about the sounding?
Yeah.
Just
All right.
whatever
So
you find interesting.
the biggest takeaway with that sounding, the OUN sounding anyways, is so the SRH at 1 kilometer, that was 1017.
And
Whenever
maybe
that
go ahead. Oh, sorry. I was just gonna say maybe let folks know what the SRH is.
Yes, so basically it helps indicate like I guess in a sense how much shear and how much spin is available in the atmosphere, how much wind shear there is. And whenever that value starts to get, even if it's like 300, 400, 500, that's still a lot.
Mm-hmm.
But 1017, that is just a ridiculous amount of shear.
Yeah, for context, just to add on there, we learn in class that typically for a tornado, you want your 0 to 3 kilometers, so from the ground up to 3 kilometers in the atmosphere. You want your storm relative helicity, which is what SRH is, and like Ben mentioned, it's just kind of a measure of how much wind shear is there. You typically want it to be at least 150 to have a chance at a tornado. So 1,000 is insane. Like, it's one of the highest values I think I can remember ever seeing.
And so yeah, SRH, the storm relative helicity, that's 1 to 3 kilometers. But another thing you want to look at, so I guess for context, right? For severe thunderstorms, you need shear, lift, instability, and moisture. And so shear is the wind change, or the change in wind direction from like the surface to some designated height above. And so for so the 0 to 3 kilometer, or surface 3 kilometer, these wind barbs here on the side, these show you the direction the wind is coming from. So the flags at the end, that's the tail. Like if you think of it of like a weather vane arrow, the tail, or like the feathers on an arrow, that shows which way it's pointing. So so this shear here is coming from the south-southeast. And so we have here at the surface a south-southeast wind. By the time you're up to 3 kilometers, that's more of a southwest. But look, by the time you get all the way up to like 12 or 15, that's just a straight up westerly flow. And so that amount of that difference from surface to even like the upper levels right here, it's a really good helper for the storm to actually get some of the vorticity it needs.
Yeah, we call that a veering wind profile. Anytime you have winds going from the east, southeast, south, and that with height turn to the west, it's a veering profile. And veering profiles are necessary for creating supercells that at least spin cyclonically. You can have some anti-cyclonic movement in there, which just means the storm spins the other way, but those tend to be far weaker and far less common.
And it's a little confusing because cyclonic refers to counterclockwise, but veering profiles move clockwise. So this like would move. I keep like trying to gesture, but even no one can see what I'm.
The interesting thing when forecasting in the southern hemisphere, it's the opposite.
Yeah. So the other side of that coin is backing wind profiles, which are counterclockwise, but they are more indicative of anticyclonic motion, which is weird to think about. But yeah, so this is a awesome textbook sounding. Look at the nose on it.
And typically, folks, I mean, that what we call that is a cap. It's a warm nose. It's a layer of warm air that's aloft in the atmosphere that's warmer than the air below it, right? So you have the old adage, warm air rises, right? Well, what happens when that warm air hits air that's warmer than it? It can't rise anymore, right? So that creates a lid for the atmosphere. But when you have, and typically that limits any storm potential. However, when you have a cold frontal system, which has a lot of forcing, right? It forces the air upward. And I believe there was recordings from the Mesonet in Norman that showed there was a rise in pressure of 5 to 6 millibars behind the cold front. And
Yes.
while that might not seem a lot, that generates a lot of lift. So it allowed these storms to punch through that. And once you get above that layer, there's nothing to stop these storms from going. And also, you have a little bit of some dynamic cooling effects due to the storms raining on that sort of cap area. When you rain into an area, you kind of bring the temperature in that area down overall, so it kind of weakens the cap a little bit. But the dynamic forcing from that cold front was really what set this thing off. I'm completely nerding out about this sounding. This is one of the
Go
most
ahead,
incredible
man.
soundings I've ever
The
seen.
amount of forcing too with that cold front, like there is a temperature inversion there and everything, but that temperature inversion didn't even mean anything. With
It's
the
also
amount
worth
of
mentioning
forcing.
that the storm was already in progress when it hit this environment, right? The storm started
Yes.
way out west and kept pushing in. And when supercells in their center cores, right, they have their own pressure perturbations. So supercells essentially act as mini areas of low pressure. And a lot of times the dynamics around that render an atmosphere that otherwise wouldn't produce storms completely useless. That cap does not matter.
Mm-hmm. Yeah, and you know, I mentioned the four ingredients, right? Shear, lift, instability, moisture. Well, we've covered all four of those, right? We have this veering profile. So there's your shear, the cold front, just like the packed pressure gradients in general, right? That lift, instability. Actually, we haven't really covered instability, but
Instability is
moisture.
kind of yeah, on the surface the instability is kind of crap for lack of a better word if you
I
based
mean,
it off the sounding.
yes. And here's my thing, right? So we have this significant warm nose. That's so this red brown-ish dotted line here, right? Everything to its right, or everything that's between that red temperature profile and it, that is sin or convective inhibition. Again, like he talked about, that's a layer that's keeping convection from happening. But when you get past that and it does finally break free, and the temperature of the air, we kind of think of it as like a little parcel or like a package of air. Once that temperature gets above what its surrounding environment, it's free to be buoyant, right? And so then this area where the red line is underneath, that is all cape or convective available potential energy. I had to think about it for a second. So that's all cape. So this is all like, if you think of it as, this isn't the scientific way you'd put it, but if you think about it as like buoyancy, right? This is all positive and this is all negative. And so once like these two kind of cancel out, what's left over is kind of your total sum. Again, not the way there would be professors snatch me bald headed for saying that, but like it's the general way I understood it, right? When I was just kind
Yeah,
of getting
and
into it.
you know there's some more work being done on what's the best way to measure cape. For example, Dr. John Peters at Penn State University has worked on some stuff called entrainment cape. The idea is the environment around a storm limits how much of that cape it actually uses
Uh-huh.
or can help it.
Which
There's
is why I don't want to interrupt you, but that's why like we have different kinds of
mhm.
cape, right? We have surface based cape, mixed layer cape, and that's because this like any one system can't use all the cape that's available to it.
Yeah, typically storms use less than the forecast amount of cape possible, except the exception to this rule that I've seen so far, based on some of the stuff I've read, is supercells. Supercells, if you look at the average vertical velocities of their updraft based on the whole two cape or square root of two cape equals there's an equation for this basically to calculate how quickly the updraft should be in this amount of cape. Supercells operate at supreme efficiency. I'm talking like 150% efficiency because of the dynamics in play within them. So I think that's a prime case of what happened here, exceeding the amount of cape that's technically there.
But again, to highlight what's weird about this is this isn't just a lone supercell. This is effectively a supercell that's embedded in a squall line.
which should typically limit some of this
Uh
because you
huh.
get
Which is why
very
it's
strong cold
very
air in
bizarre.
behind these supercells that typically wraps around the cyclone very quickly. And when supercells have or tornadoes have their warm air cut off, it ends up killing the tornado because tornadoes are essentially the product of the gradient between warm and cold air. They need that balance between the warm and cold air to form.
Mm-hmm.
But in this case, the supercell was very well maintained. It kept sort of that RFD rear flank downdraft, which is where all the cold air is to the southwest of the storm on the backside. It kept it from fully wrapping around, and it was certainly something to watch on radar. That's for sure.
Mm-hmm. Yeah, it really just a bizarre instance. Um, but it wasn't just the tornadoes. I'm gonna segue a little bit. It
Yeah,
wasn't just the. If we go back to the storm reports, wasn't just all tornadoes. In fact, you'll notice most of these little blue dots are wind reports, and that's because this was an enormous wind bag. Like this was
yeah.
a really potent wind generator.
Just to
Here,
kind of explain why that is. I'm sorry, I don't mean to
no,
cut
go
you off.
ahead,
Just
go
to
for it.
explain why that is very quickly. Like we mentioned earlier, there was a lot of really strong winds aloft in the atmosphere, and with the way that this system evolved, when you get very strong downdrafts on the backside of these storms, it can bring that strong air aloft, which wasn't that high up. The lower level winds were extremely strong, say 850, 800, 700 millibars, so a few kilometers up in the atmosphere. You can bring that down very easily to the surface in these downdrafts, and that's what happened here.